Okay, let's unpack this. In our ongoing journey beyond Transformer, we've been systematically tracing the evolution of sequence models. We've gone deep into the capabilities of state space models, SSMs.
Right.
And we spent quite a bit of time understanding Mamba, haven't we? Especially how it excelled in that causal left-to-right processing.
Yeah, Mamba really did push the boundaries there,
Mm.
especially with very long sequences. It offered a compelling alternative to the Transformer's scaling issues.
Exactly, that quadratic scaling and the fixed context window. We've talked about how SSMs, with their finite states, act more like a sort of continuous brain.
Always on, processing inputs, updating memory.
Right. Capable of that infinitely long, but maybe slightly fuzzy recall, which made Mamba super efficient, especially for autoregressive tasks.
Predicting the next thing based only on the past, essentially.
Precisely.
But, and this is really fascinating, isn't it? So many real-world tasks, they demand more than just that one-way street, that causal understanding.
You mean things where you need the whole picture?
Exactly. Think about masked language modeling, MLM. To predict a missing word accurately, you absolutely need context from both sides. What came before, and crucially, what comes after.
Yeah, a causal model just can't see the future words.
It literally can't.
Yeah.
Or consider image classification. When you look at a picture, your brain doesn't just scan left to right, top to bottom.
No, it's more holistic, right? You
Right.
grab information from everywhere at once.
Precisely, simultaneous integration. And these scenarios, they inherently benefit from a bidirectional perspective. That's a key area where traditional causal SSMs, Mamba included, well, they have a gap compared to something like a transformer.
Even with the transformer's own issues, its attention mechanism naturally handles global context.
Right, and that performance difference on bidirectional task really highlights an essential need. Models need to be capable of bidirectional processing to truly generalize across different AI applications.
That really is the crux of it. And that leads us directly into today's deep dive. Hydra. Now, this isn't just another small tweak on SSMs. It feels like a more deliberate leap.
It is. Hydra is framed as a natural bidirectional extension of Mamba, specifically engineered to tackle those non-causal problems where purely causal models just don't quite cut it.
So our mission today is to really get into how Hydra pulls off this bidirectionality. It uses a powerful mathematical idea, something called quasiseparable matrix mixers. We need to unpack that.
We do.
Uh-huh.
And we'll look at the architecture, how it manages to read sequences both ways.
And then critically, the results. What does its performance on benchmarks like GLUE and ImageNet1K tell us about where versatile sequence models are headed?
Yeah, the empirical validation is key here. Expect some deep math, but hopefully presented in a way that shows its practical power.
Sounds good. Let's dive in. Okay, so to really grasp what Hydra brings, let's quickly revisit Mamba's core strength. As we covered in episodes 2, 3, and 4, Mamba 1 and Mamba 2 were built on those foundations from Hipio and S4.
Right, the focus was heavily on efficient causal processing, left to right.
Perfect for autoregressive tasks, generating text word by word where the next word only depends on the previous ones.
Or time series forecasting, perhaps? Information flows one way.
Exactly, and Mamba's architecture nailed this, processing huge sequences with linear time complexity, a massive advantage over attention's quadratic cost.
In that internal state, like you said, that updating brain, maintaining a fluid, long memory.
But that very strength, that causal focus, becomes a limitation for a whole other class of problems.
A very important class. Problems needing a full understanding of the entire sequence, not just the past. This is the core issue Hydra tackles.
Let's take masked language modeling again, MLM.
A cornerstone for pre-training, right? You mask a word, the model predicts it.
To do that well, you need the surrounding words,
Yeah.
before and after.
Yeah, absolutely. A purely causal model is flying blind for the words that come after the mask. It's fundamentally disadvantaged.
The crossword analogy was good, only seeing clues to the left. You wouldn't get very far.
You really would.
And it's not just language, is it? You mentioned image classification.
Right. We don't see images causally. We perceive them globally. Shapes, textures, relationships across the whole image all at once.
So a model needs to integrate information from all parts simultaneously for robust classification.
Exactly. And this is where we see causal SSMs, even efficient ones like Mamba, show noticeable performance gaps compared to architectures that handle bidirectionality better.
Like transformers or specifically designed bidirectional models.
Correct. This performance disparity isn't trivial. It highlights what the paper calls an essential need for models to be capable of bidirectional sequence processing.
If we want models that can generalize beyond generation into tasks requiring deeper understanding or perception,
Precisely. Which leads to the big question.
how do you give SSMs this crucial bidirectional power without sacrificing their efficiency?
Yeah, that linear or subquadratic scaling is their killer app, isn't it?
Yeah.
You don't want to
Sure.
lose that.
So the challenge is getting the best of both. SSM efficiency plus bidirectional understanding.
And that's exactly where Hydra comes in. It's designed to bridge that gap.
Okay, so this is where Hydra starts to really carve out its own identity. It's explicitly called a natural bidirectional extension of the Mamba model.
Right. And the key innovation, the engine driving this, is its parameterization. It's built as a quasiseparable matrix mixer.
Quasiseparable matrix mixer. Okay, sounds technical. Let's break that down. What does it actually mean?
Well, let's start with quasiseparable matrices. Think of them as a more general, more powerful class of structured matrices. They actually generalize two important types. Semiseparable matrices, which we know are core to SSMs, and also low-rank matrices.
Okay, refresh us quickly on semi-separable matrices. We touched on this with Mamba 2 and SSD.
Sure, semiseparable matrices have this specific structure where if you take any submatrix from the lower triangle, below or on the diagonal, its rank is capped by the SSM state dimension n.
And that structure is what makes them computationally efficient, right?
Exactly. It's fundamental to Mamba's speed and performance. The Mamba 2 paper, with structured state space duality, really drove home that SSMs are parameterized by these semi-separable matrices. SSD showed this elegant equivalence.
So computing the SSM forward pass is like a very structured, very fast matrix multiplication.
Precisely. So quasi-separable matrices, by generalizing these already powerful semi-separable ones, offer a richer mathematical structure, a potentially more expressive way to model sequence interactions.
So moving from semi-separable to quasi-separable is like upgrading the mathematical toolkit,
Yeah.
allowing for more complex operations.
In a sense, yes, it provides a theoretical extension. But the really clever part is how Hydra uses this generalization without losing efficiency.
Right, the efficiency is crucial. How does it manage that?
This is the core insight. The matrix multiplication for these more complex quasi-separable matrices can be cleverly decomposed into two operations of semi-separable matrix multiplication.
So it breaks down the harder problem into two instances of the easier, already optimized problem.
Exactly. And these two semi-separable multiplications are combined using very simple functions, flip and shift.
Okay, flip and shift. Let's visualize those.
Sure. Take a sequence, say 1, 2, 3, 4. Flip. Just reverses it. 4, 3, 2, 1. Simple reversal.
Got it. Like reading backward.
And shift typically shifts everything one step to the right and pads the beginning, often with a 0. So 1, 2, 3, 4 becomes 0, 1, 2, 3.
Okay, so how does combining two semi-separable ops with flip and shift give you bidirectionality?
Well, you effectively run one efficient causal SSM pass on the original sequence, forward. Then you run another efficient causal SSM pass on the flipped sequence, backward.
So processing the flipped sequence is like processing the original sequence from right to left.
Precisely. Then you use shift and flip again to carefully align the results from these two passes before combining them.
That's clever. You get information flowing both ways, but you're only ever using the fast causal SSM machinery.
Exactly. That's how Hydra achieves that full bidirectional context while maintaining subquadratic complexity. It's an elegant decomposition.
Now, this idea of matrix mixers. Let's zoom out again. We discussed this framework back in the Mamba 2 deep dive.
Yeah, it's a really unifying perspective. The idea that many different sequence models, deep down, are performing a transformation that looks like y equal mx.
Where x is the input sequence, y is the output, and m is this mixer matrix that defines the transformation across the sequence dimension.
Right. And it's surprising how many models fit this mold.
Not just the obvious ones like MLP mixer or FNIT.
No, also things like linear attention, S4, H3, TNN, CKCon, Kaleidoscope, Monarch, and Mamba itself.
So this framework acts like a kind of Rosetta Stone, showing underlying similarities between seemingly different architectures.
Exactly. It provides a powerful lens for understanding how these models mix information on the sequence. It reveals the structure within that M matrix.
And Hydra fits neatly into this framework too, doesn't it? It seems like it was designed using this framework.
Very much so. The paper explicitly states that Hydra demonstrates that the matrix mixer framework can systematically design new, versatile sequence models.
So it's not just descriptive, it's prescriptive. a way to actually build new models with desired properties.
That's the implication. By choosing the right structure for your mixer matrix M, like making it quasi-separable for bidirectionality, you can engineer specific capabilities into the model.
That's powerful, like having architectural building blocks.
And the framework also helps us identify key design dimensions that differentiate these models. Two important ones mentioned are sequence alignment and data dependency.
Okay, what's sequence alignment?
It's about whether a model trained on a certain sequence length can generalize effectively to much longer sequences without retraining.
Ah, so avoiding hard context limits like in vanilla transformers.
Right. It often comes from having learned parametric functions that can be applied repeatedly or extended rather than fixed positional embeddings, for instance.
Makes sense. And data dependency.
This is huge. It means the way the model mixes information, the effective M matrix, isn't fixed, but changes based on the actual input data X.
Like attention, where the attention scores depend on the specific query and key values.
Exactly. Attention is highly data dependent, and that's seen as key to its power. Hydra, through its specific design as a quasi-separable mixer, brings this kind of dynamic, data-dependent mixing into the realm of SSMs.
So SSMs can now adapt their internal processing based on the input, much like attention does.
That's the idea.
Yeah.
And crucially, Hydra does this while aiming to keep the efficiency benefits of SSMs. It's about adding that adaptive power without incurring the full quadratic cost of attention.
That feels like a significant step, potentially bridging the gap between SSMs and transformers in terms of expressive power.
It certainly aims to. It makes SSMs more versatile by incorporating this key feature previously associated more strongly with attention.
Okay, we've covered the theory. Bidirectionality needed, quasi-separable matrices provide the means via the matrix mixer framework. Let's pull back the curtain on the actual Hydra architecture. How do the pieces fit together operationally?
Right. If you look at a diagram like the one in the paper, you see the input X comes into a Hydra block. The first thing is it gets prepared for this dual processing.
Forward and backward passes.
Exactly. There's a projection, projatchet, to get the dynamic step sizes, which are critical for SSMs adapting to the input. And other components, discretize and discreticy, get the core SSM parameters, ABC, ready based on these dynamic step sizes.
Using the structured state space duality, the SSD mechanism from Mamba 2.
Precisely. The core computation relies on the efficient SSD operation. So first, there's the forward pass, IFSSDX, basically. Standard causal SSM processing, reading left to right, captures past context.
Okay, that's like the Mamba part we know, now the backward pass.
Here's the clever bit. It uses the same SSD machinery, but applies it to XB, which is the flipped input sequence.
So XB always flip.
Right, so you calculate YB equal SSD XB.
Right.
Because the input is flipped, this effectively processes the sequence right to left, capturing future context relative to the original sequence order.
It's elegant because you reuse the same efficient causal engine just by manipulating the input.
Exactly. It leverages the symmetry inherent in the decomposition of the quasi-separable matrix.
Okay, so now we have IF, forward context, and YB, backward context, but based on the flipped sequence. How are they combined?
They get careful alignment first. The forward output REF gets shifted, right? REFF gets shift. YF.
To align it properly for summation.
Yes, and the backward output YB needs two steps. It's shifted, shift YB, and then critically, it's flipped back. YB is flipped, YB.
Ah, flipping it back puts the backward context in the correct order relative to the original sequence X.
Precisely. Meticulous alignment.
Mm-hmm.
Then finally, you combine them. The output Y is the sum of the aligned forward part, the aligned backward part, and a direct connection from the input XYF plus YB plus X prod GX. That prod GDS part represents the diagonal elements of the quasi-separable matrix, allowing a kind of input-dependent residual connection.
Which is a standard technique for improving gradient flow and performance in deep networks.
Right, so you get forward context, backward context, and a direct path for the original input, all combined.
And this whole structure ties directly back into the structured state space duality SSD framework we explored with Mamba 2.
Absolutely. Hydra is built directly on SSD. Remember, SSD show that certain SSMs were equivalent to a form of causal linear attention, represented by semiseparable matrices. This allowed for efficient computation using the matrix mixer idea.
So SSD provided the efficient engine for the causal part.
Yes, and Hydra extends this by showing how to combine two of these efficient causal engines, one forward, one on flipped input, to achieve bidirectionality, leveraging the mathematics of quasi-separable matrices being decomposable into two semiseparable ones.
So it inherits the efficiency wins from SSD and Mamba 2, like the subquadratic complexity.
That's the goal and the claim. By sticking to operations based on semiseparable matrix multiplications, it avoids the quadratic cost of dense attention, even while providing that bidirectional view.
It really highlights how powerful these structured matrix perspectives are for designing efficient yet capable models.
It truly does. It shows a systematic way to build more complex functionalities from these efficient primitives.
Okay, we've gone through the architecture, the math, quasi-separable matrices, decomposition, SSD connections. It sounds really elegant on paper, but here's the crucial part, right? Does it actually work? How does Hydra perform when you test it on those non-causal tasks it was designed for?
Exactly. Theory is great, but empirical results are where the rubber meets the road. And the evidence presented is, well, quite strong. Hydra consistently shows superior performance on these specific bidirectional tasks, validating the approach and the power of the quasi-separable matrix mixer design.
Let's start with masked language modeling, MLM, on the GLUE benchmark. We keep coming back to MLM because it's such a clear test of bidirectional understanding.
It really is causal model struggle inherently.
So how did Hydra do against established models like BERT?
It actually outperforms BERT by 0.8 points on the GLUE benchmark. The average score reported is 84.3 for Hydra versus 83.5 for BERT-base.
0.8 points on GLUE average is definitely significant. That's not noise.
No, it's a solid improvement. And importantly, it also beats other bidirectional alternatives tested like MLP Mixer, FNet, and the M2 variant on both the C4 pre-training perplexity and the final GLUE scores.
And this was a fair comparison. Same parameter count, roughly.
Yes, the experiments were carefully set up to align with BERT-base, around 110 million parameters. Hydra used 23 layers to match that parameter budget compared to BERT's 12 layers.
So, roughly equivalent capacity. The gains seem architectural, driven by the bidirectional SSM approach.
That's the conclusion drawn. It highlights the effectiveness of the Hydra block itself.
Okay, very impressive on language understanding. What about vision, image classification on ImageNet 1K?
Another standard, tough benchmark, and often dominated by CNNs or vision transformers.
How did Hydra fare here, especially since it treats the image as just a flat sequence?
Remarkably well. The paper states Hydra exhibits superior performance in image classification. It beat the ViT base model, a strong transformer baseline, by 2.2% in top 1 accuracy.
2.2%, that's substantial.
It is 81.0% for Hydra versus 78.8% for VT base top 1, and also 1.1% better on top 5 accuracy.
And this is without any 2D specific structures, no convolutions, no patch interactions built in?
Correct. It's simply flattening the image into a sequence and letting the Hydra blocks process it, which makes the result even more striking.
Wow. How did it compare to other sequence models applied to vision, like S4ND?
It surpassed S4D too, even though S4ND is an SSM variant specifically designed for image data. Hydra achieved 81.0% top 1 compared to S4ND's 79.4%. That's a 1.6% margin.
So it beat both a standard vision transformer and a vision-specific SSM.
Based on the reported results, yes. The comparison involved taking the ViT-base architecture and swapping out the transformer blocks with S4ND, Hyena, Mamba, and Hydra blocks to compare their core sequence mixing capability directly.
These results really drive home the point, don't they? That the matrix mixer framework, used systematically, can yield models that are highly competitive or even better than established architectures like transformers, especially on these non-causal tasks.
Absolutely. It's strong validation for the design principles behind Hydra and suggests SSMs are becoming truly versatile competitors across different domains.
Yeah.
Hashtag tag outtag outro.
So let's try and synthesize this. What's the big takeaway from our deep dive into Hydra? We've explored this model that pushes state space models beyond their traditional causal comfort zone.
Yeah, it's a really significant development. Hydra's core contribution is this natural bidirectional extension of Mamba, achieved through that clever parameterization as a quasiseparable matrix mixer.
That sophisticated math, the decomposition using flip and shift, allows it to tackle tasks needing full sequence understanding, past and future context.
And critically, it does so efficiently, leveraging the speed of the underlying SSD mechanism.
And the empirical results back it up, outperforming strong baselines like BERT on GLUE and VIT and even S4ND on ImageNet.
Right. It's not just a theoretical curiosity. It delivers tangible performance gains on important non-causal benchmarks.
This really feels like a statement that SSMs are no longer just niche models for ultra-long sequences or causal generation. They're becoming general-purpose sequence model contenders.
I think that's fair to say. They can now compete effectively, sometimes even winning, in territory previously dominated by attention mechanisms, and they retain that crucial scaling advantage.
Connecting this back to our series theme, it really underscores the power of that matrix mixer framework you mentioned.
Absolutely. As a systematic tool for designing new architectures with desired properties, it's guiding research towards more principled model development.
And it highlights the ongoing rapid evolution of SSMs. They're clearly a compelling alternative or complement to transformers, pushing towards more efficient and adaptable AI.
The landscape is definitely becoming more diverse, which is exciting.
Which brings us to a final thought to leave with you, our listener. Hydra successfully unlocked bidirectionality using quasiseparable matrices. It makes you wonder, doesn't it? What other hidden mathematical structures, what other generalizations within this matrix mixer framework might still be undiscovered?
Right. What new mixer matrices are waiting out there?
Exactly. What new capabilities could they unlock? Perhaps models that learn even more effectively from raw, unstructured data bytes, audio, video, in truly end-to-end bidirectional ways we're only just starting to conceive of.